Hello, and welcome to another of my Thursday Toast recordings. Yet again, not going out on a Thursday, not recorded on a Thursday, and I appear to be out of port. Actually, that's a lie. The port's in the other room. I'm just lazy and can't be bothered to go and get any. So, today I was going to answer a question from my last video on the brain injury. This one was from King's Rook and is basically asking how space affects the body and performing medicine in space. I think he had visions of the Star Trek 6 Undiscovered Country thing where the blobs of Klingon blood are floating in space, but yeah, we'll come on to that. So to try and answer this, I have gone to what are probably going to be some fairly unreliable sources. I thought NASA and articles from Science and the BBC were the main ones. Oh, and a UK government website. So NASA certainly says that their problems for human body in space fall into 5 categories, and they are gravity or lack thereof, isolation and confinement, which is a psychology issue, the hostile and closed environments you're in, radiation, that's kind of, the risk of sounding terrible, the cool one, and your distance from Earth. So I'll go through those and then I'll come on to some of the other bits. So the first thing is the gravity fields. So in microgravity or zero gravity, it's microgravity or free fall, a number of things get affected. So your spatial orientation, your head-eye and hand-eye coordination, sense of balance, locomotion, all get affected. Motion sickness is apparently really quite common. Now, those can be mitigated with fitness regimes, and what those are mostly doing is to put strain on the body to try and mimic the normal effects of just standing there against gravity, frankly. So astronauts do, I believe, typically 2 hours of fitness a day if they're on the ISS. Other things that happen are your bone density drops, and that drops at a rate of about 1% a month, as opposed to if you're elderly and get dealt a bad card, you might drop 1% bone density per year. Similarly, your muscle strength and stamina drops and causes a great deal of deconditioning. One person was quoted as saying it was a bit like getting somebody to go from being like a 20-year-old to a 60-year-old over in the space of 3 months, and with 40% muscle loss and potentially needing rehab for a year after a lengthy ISS mission. You get, and the heart is a muscle, and that can also get deconditioned, and that would also be a problem. Then we haven't necessarily fully explored that, and there is an increased rate of arrhythmias noted amongst astronauts, or there are arrhythmias noted, and that could be because the blood flow doesn't have gravity affecting it. Don't know. Other things you get. So as part of the bone density dropping, that's due to bone demineralization, and that calcium your body is very good at dealing with. or other bits of your body are very good at dealing with. So you pee it out. The problem with that being you get kidney stones, because also apparently in space you tend not to drink very much, because you know that very soon after takeoff, what you're drinking is somebody else's pee. To be fair, that's also supposedly true of Thames water, which I drink, but that's not the point. Actually, no, I have Surrey and Sussex water, I think. I wonder if it has the same urine content. Never mind. So yeah, there's that, and another big issue that seems to come up is you get fluid shift, because again, you don't have gravity, and that can particularly increased pressure in the head, because actually we've got nice, great big blood vessels going up into the head, and then we expect, because it's fighting gravity, and then the stuff going down, it gets smaller, and then but what the body's used to doing is then also having things draining out with gravity, and the legs and things actually help to pump stuff back up. And that can actually affect the pressure in the eye, and that can lead to changes in your visual acuity and things. So that's not great. And apparently one of the things they're talking about doing for that is looking into kind of almost a reverse G suit, to actually, so where a G suit stops all the blood from rushing into your legs and pooling there, this is trying to actually keep the blood in your legs and make it have to work harder to get back, so that you're actually having more in the legs than in the head. Another key thing is going to be nutrition and digestion. So food, maybe to some extent gravity. Certainly, apparently, sense of taste gets thrown. There's weird things happen with smell, and people often apparently don't drink enough, so that's going to cause issues. And so you're probably going to end up wanting to monitor your fluid intake and output. So check how much you're peeing, and probably also checking what you're peeing out to make sure that bits of your body are actually coping okay. So that's quite a lot, and that's just really looking at the gravity effects. Oh, and the idea for trying to deal with the hand-eye, head-eye coordination, spatial orientation, all that kind of stuff, is to kind of do what might be called pre-problem rehabilitation, almost, where you are going to kind of be doing some possibly standardized, possibly not so standardized tests to keep those things lined up as things change and as your body changes. This will also have an issue with some of the psychological or mental side of things, which brings me neatly on to number 2, which is the kind of isolation and confinement and the massive psychological effects that's going to have. And there's a lot of work being done on that, and the evidence for that you get with it is not brilliant for space flights. And they're typically looking at pretty small groups, so no more than 6. I will come on to this. And there's also lots of issues with circadian rhythms and kind of the effects on the body from prolonged stress, and if you're not sleeping properly and all those sorts of things. And I think food is going to come into that, because actually, if you have rubbish food, that's going to be a big issue. So there's that, and your health. And really what you need to be doing for a lot of these things is kind of monitoring for it and then doing something about it when you can. Next is the kind of other side of this, which is the hostile or closed environment. Now, there's quite a few things with this. So you've got what I would call the microbiological ecosystem. So that is the bugs. Bearing in mind we are, some estimates put it that there are 10 times as many bacteria in our guts as there are cells making up our bodies. So we're really a means of a load of gut bacteria to move themselves around from food source to food source. And the problem is some of those bugs, at least, if they get in the wrong place, do bad things. So you are taking problems with you. Another thing you can have is if you're particularly prolonged stress and things like that, and there seem to be some effects on the immune system as well, you get risk of reactivation of viral illnesses like Epstein-Barr, which is oh goodness me, why can I not remember what that one is? Anyway, Epstein-Barr and shingles, which is chickenpox coming back. Epstein-Barr, I'm sure, will come to me. So, and lastly, you kind of have the risk of contaminants getting into your air supply and things, because it's all going to be processed and things, and you've got risks of problems getting in like that because you're going to have machinery and oils and all that kind of stuff, and air scrubbers and goodness knows, and water scrubbers and goodness knows what. So that's another risk. So you're going to be wanting to test your air, your water, blood, urine, saliva, try and reduce stress. So that's going to be the sleep, the team mechanics, all those sorts of things. Glandular fever, that's Epstein-Barr. And yeah, so that one, as with some of the psychological stuff, you kind of have to watch and wait. Now, with both of those, we have the advantage that we have been sending humanity, or at least Western types, have been sending people on long, isolated journeys for a long time. You going back to the early age of sail, you had people sailing for weeks, months, in fact, at a time, isolated. So a fairly standard sea voyage to India from Britain in the 1780s or 90s might take 6 months, and you wouldn't put in necessarily anywhere en route. So you're completely self-contained, and that includes water, which is possibly why they all drank beer when they weren't having rum. But it's also why they all got scurvy. So, but we've also then moved on, and we've had polar expeditions that have lasted years because they got lost, but they had supplies. We've got people going to Antarctic bases and overwintering there. We've got people on nuclear submarines, and particularly the SSBNs, the bombers or boomers, don't like having to come up often and just sort of go, hello, or we just thought we'd have some fresh air, maybe pick up some fresh fruit and veg. They apparently they like to be stealthy for their 3-month deployments. Who knew? And we've got data from that. And actually, because we've had these Cold War and since patrols for decades now, with sending people under the sea in particular, we've had opportunities to observe. Now, the difficulty is that what we haven't done in the modern era is do this for as long as, say, a Mars mission is going to be, which is the kind of, I think, where a lot of this stuff is going to when you look at the real life stuff. You're kind of talking about what's going to happen on a Mars mission. So, and Mars mission is anticipated to take 30 months, 500 days. Yeah, a long time. There's some real issues in that, and this is going to come on to what I'm going to be talking about. So the radiation. Now, space radiation, I get to use some really cool terms. So on the ISS, an astronaut or cosmonaut is exposed to 10 times the natural background radiation they might get on Earth, just because they're that bit further out from the magnetosphere and all that kind of stuff that protect us. If you're going to Mars, you're completely out of that. So you're going to get a lot more. And what they did was on a probe that was launched in November 2011, the Mars Science Lab, which had possibly the Mars Explorer robot on it, took a radiation monitor along, and they got recordings pretty much every day for the journey, which was then published in 2013 in Science. So we've got some ideas. So you've got risk from radiation in terms of radiation sickness, and you've got risk from kind of causing later problems with other than that. And thirdly, I run out of hands because I've not had lots of radiation exposure. Thirdly, you've got the kind of radiation poisoning and radiation sickness potential. So kind of you get, so going back to my brief thing about acute and chronic, so you get acute and chronic radiation diseases, and you have the risk of cancers. Now you're dealing with two things which are going on in terms of the energy and whatnot. You've got the solar energetic particles, which are particularly coming out with solar eruptions. And if you're lucky, you might get an hour's warning on that, and that's going to be a big burst of radiation. And they're actually talking about the astronauts building what sound like it's basically going to be a cushion for a pillow fort. Basically, the astronauts are just going to heap all of the kit on top of themselves, because actually what happens with these solar energetic particles is they whiz through. They've come out of the sun, and they're from a solar flare type thing. They're whizzing through, and they hit something, and they shed energy. They spread the energy, and that's what causes damage. So if you have lots of shielding, it's going to hit that, and it's going to dissipate the energy. And this is why I will come on to what I would actually want to take with me on a mission to Mars. But that's one of the big issues. Now you're getting problems both from the immediate effects of the radiation and also a kind of gradual build up of the dose, and that's on both equipment and people get damaged by these things, interestingly. So total dose is also an issue. Now, radiation is measured in two ways. You talk about grays and you talk about sieverts. I cannot for the life of me remember what the difference is, and I didn't make a note on it. If you want to know about that, we can do something else about it, or you can find somebody who might actually know about these things. But I'm going to talk about millisieverts because that's what all the stuff I looked up said. So an average person in the UK, this is from a UK government website, bit of data published in 2011. I'm getting some of this, and some of it's from the NASA stuff. So average person in the UK has an exposure of 2.7 millisieverts per year. Interestingly, in the US, it's 6.2 millisieverts per year. Exposure on the ISS generally works out at about 150 millisieverts per year. And Apollo and Skylab astronauts were getting 1.2 to 1.4 millisieverts per day of exposure. Now I'm going to run through a few numbers to give an idea, and I'll keep trying to refer back because this is one of those things where a table would be helpful, and I might even try and put one in when I'm editing this. So a chest X-ray is 0.014 millisieverts. A transatlantic flight is 5 to 6 times more radiation than that. That's flying, London to New York or something. A scan of the a CT of the head, this is the 2011 data, and machines have probably got a bit better, is 1.4 millisieverts. A CT scan of the chest is 6.6 millisieverts, so 3 times what your average Brit gets, or about a year of being an American. Apparently, the average radon dose in Cornwall is 6.9 millisieverts per year. If you're a nuclear industry employee, you're allowed to get up to 20 millisieverts exposure per year, and these are the people who wear the monitors. You would get acute radiation effects, where you'd feel sick and you'd see some really marked changes in blood work at about 1,000 millisieverts, or 1 sievert, I guess. And a dose of radiation that's going to kill half the people exposed within a month is 5,000 millisieverts. Now, to put this in, so just to remind you, so if you work with any sort of nuclear industry in the UK, so anything, so if you're one of the radiographers, if you are one of the I don't know, work at a nuclear plant, but actually we use X-rays a lot, and there's a lot of things which are a surprising number of things which are radioactive that are used because it's useful for doing things like checking how thick a plastic is and things like that. So it's actually used in a lot of things, hopefully in boxes, but if you're near it all the time, it counts. So the most they're allowed to have is 20 millisieverts per year, and normal ISS exposure would be maybe 70 millisieverts in a year. So that's a bit worrying, but I guess you're not going to be on the ISS every year. But there's a couple of people, Scott Kelly and Mikhail Kornienko, whose names I may have, one of those names I may well have got wrong. They managed 340 days. But as I said, we're looking at sort of 30 months, which I haven't worked out how many days that is. Different people are using different things, but it's a worryingly long time. And when the Mars Science Lab probe went and travelled, it took 253 days to cover the 560 million kilometers. Or was it 56 million kilometers? I can't remember. It's a long way. It was picking up, varied from about 1.5 to 2 millisieverts per day, every day, times 250, that's 500 millisieverts. That's quite a lot. That's just one way. You're then going to stay around Mars. Okay, it'll be less, but Mars doesn't have anywhere near as much gravity. It's, I think, 1/6. I can't remember. I did know this at one point. I'm not a space scientist. I'm not a space doctor. That's quite a lot. And then you've got to come back, which we didn't do with that Mars rover. Oh, the poor Mars rover. I still feel sorry for him. He's a good boy, good rover. And there are also these bursts of solar energetic particles. And it encountered 3 events, and that gave it a total of 24.7 millisieverts. So that's the equivalent of having your chest scanned 4 times, give or take. But it's the galactic cosmic radiation, or the galactic cosmic rays, that are the big problem. That is so cool. Galactic cosmic radiation and rays. I mean, you actually get to say things like this. It's so cool. And they're the things which are giving you the kind of couple of millisieverts per day. And that's the problem. The kind of 1.5 to 2.2, 1 or 2 millisieverts per day, every day, just grinding away at you and all of your organ systems. And one of the things that's been being looked into is that it looks as though microgravity may, we don't know, the results when I looked at a 2017 paper from NPJ Microgravity, it looks as though it's not clear, but there may be an effect from microgravity on the function of your DNA damage repair mechanisms. As well as the radiation damaging your DNA, which is what causes cancer, but also can cause other things, you're also getting an effect from them being in microgravity on your body's ability to repair that damage, and so recognize it and deal with it. And that's not really been quantified very well. And that's a potential worry. Now, the other thing is, so radiation can also cause damage to your other organs and do other bits, and there are suspicions that you're going to potentially see premature cardiovascular disease, increased rates of things like Alzheimer's. So you're potentially just having an ongoing level of low-grade damage to lots of bits of you that is going to add up. And the problem is it's going to add up quite a lot. So that's the other side of the radiation badness. So the radiation, that's a kind of a worry. Now, the 5th point, which was made by NASA in their thing, is the distance you've got from Earth. So you've got to take everything with you. You're not going to get any fresh food, no option of that whatsoever. And you need to go, well, what am I going to take with me? And a 2016 BBC piece was talking about we'd want something that would be able to lift maybe 130 tons into orbit, to then put 40 to 50 tons in past the low Earth orbit as part of getting to Mars, and that's not easy. You've got people who are going to be struggling to sleep. You're going to need them to do 2 hours of exercise a day as well, unless you can find a way of getting something that'll do that at least partly in their sleep. And the logistics are going to be a nightmare. Now, one potential game changer with logistics would be water. Ideally, if we can get water early or close, like at the moon, which is a few days travel away, rather than, a long way away like Mars is, which is 6 months, 250 days, depending how fast you go, depending what time you go. And you're going to have to weigh up the risks in terms of your timing of kind of getting there quickly, getting back quickly after your time there, and timing it with solar flares, versus if you spend longer out there, you're going to be exposed to more radiation generally from the galactic cosmic rays. Oh, such a cool term. quite pleased I've got a nice atmosphere and magnetosphere to protect me from them though. But if you could get water a lot closer, bring an ice asteroid, it's a game changer, because suddenly it's a great bit of shielding. You break it down, you get hydrogen, oxygen. So suddenly you've got an oxygen supply, and you put hydrogen, oxygen together again, and you've got kind of a nice reaction. Hydrogen also best thing for fusion. It would be really cool, and it would allow you to potentially be growing crops en route as well, because you could actually, really crack on. But you're going to be dealing with a closed loop on this long distance. That's a big bit. You've got a closed loop of things, and you're going to have to get energy in and keep yourself going for a long time on these rations. And there was an interesting thing about different foods when I was having a look at this on Wikipedia about the different foods people take up. So the Russians take up borscht, but not vodka, but caviar. Alcohol doesn't seem to work well in space, or at least some alcohols, because of the way smells can promulgate. It can lead to quite bad nausea, apparently, because of the way the smells are different in space. So that's a potential worry. So you don't not necessarily want to take alcohol. The Korean took kimchi. The Chinese person took some really lovely sounding stuff, some of which I hadn't heard of, and I didn't write down in my notes because I was supposed to be doing something about medicine. The Italian took coffee, and I cannot believe that there have been British astronauts. They must have taken tea. I mean, it's just a given. They must have had tea with them. I can't imagine them not. I heard an interview recently with Tim Peake. I think he's got an autobiography out. And yeah, I didn't pick up whether or not he took tea with him, but he's just got to have taken tea with him. It's just, can you imagine British people without tea? Then again, if you can't get the proper milk for your tea, it's tricky. Right. Next thing I just wanted to talk about was getting medical treatment during spaceflight. So this one, slightly annoyingly, the main link on the Wikipedia page seemed to be half broken, but it seems reasonable. So the main issues that have happened in space and that they've kind of known about are arrhythmias. That's when the heart rhythm goes a bit weird. Mostly harmless ones, some which have been a bit of a risk. You've had people having kidney stones. You've had people with venous thrombosis because the circulation isn't working properly, so that's DVTs, PEs. They've had people have infections. Other things that have come up and which they've worried about, particularly because they've happened to people on things like the submarines and the Arctic bases, have been things like heart attacks, because even amongst young people, they can happen. Strokes, same. You get trauma, so people get injured, and you potentially have to patch things up. You get broken bones, amputations, bleeding. You have to stop. This is your blood going, but you just get a little vacuum, and it probably wouldn't be as exciting as all that. If you really hosed out, you just get a bigger vacuum. You might get some interesting exposures to toxic substances. If any of the kit goes wrong, your food processing, your air processing, your water processing, just some of the kit going, especially if you've got lots of scientific analyzing machines, they're going to potentially have nasty acids and other reagents in there. You're going to potentially get chemical burns, electrical burns. You could get some interesting things if people are doing EVAs. You can get interesting barotrauma, so things like the bends from going into a sudden low pressure state, where basically gas that is dissolved in you at this pressure. If you go to a lower pressure, the gas doesn't want to stay dissolved. It wants to come out. And the problem is it tries to do that inside your body. And that's the bends. And it's called the bends because you are just bent because it comes out in your joints and is really painful. And you can go mad and go blind because it will affect your brain and the eyes, but also the visual cortex in the brain. That all sounds pretty bad. And yeah, not good. And there's things that you can do with gases, and at least these are things which we kind of understand. I mean, radiation, to some extent, we understand radiation. We understand the radiation in the sense of the particles and the waves, and some of the things that can't be sure if they're waves or they're particles or they're a bit of both, unless you stop them and ask them, in which case they get very uncertain. Those things we understand. What we don't always understand is the effect on complicated systems like us and potentially on computers. So on the equivalent isolation things, Antarctic submarines, things like that. Things which they've come across that are the commonest problems have been dental problems, dental issues. I mean, this is an issue a lot of the time, that tooth problems these days, they generally won't kill you as they used to pre-antibiotics, but they can be cripplingly painful. It was a huge problem apparently before, just at the start of World War One. There was a massive lack of dentistry for the British Army, and supposedly lots of people just went to a dentist, got local anaesthetic because they had anaesthetic, and just had their teeth pulled out, all of them, and got a set of dentures made. No idea if that one's true, but it's what I've heard. And on 100 Royal Navy Polaris patrols, which are only probably about 3 months, we're talking about going away for 10 times as long, so much more chance of having tooth problems, and goodness knows what it's going to do to your tooth enamel and things. Being in microgravity for that long, 100 Polaris patrols, they ended up doing 30 fillings and 7 tooth extractions. It's also apparently the commonest reason people need to be extracted from, if you'll pardon the pun, from these bases in Antarctica, why people have problems on nuclear boats, all those sorts of things. So that's a big issue. Then you just get things like appendicitis and some of the other surgical problems. So how would I deal with this? Well, knowing what I know about medicine and having read about the radiation and all the other things, I wouldn't want the space battleship Yamato, although the armor would be quite cool to get there. I'm thinking more space HMS Unicorn, which I hope Alex Clark will appreciate if he's bothered watching this far through. She was a maintenance carrier, so basically she had the fabrication stuff to make just about anything you need. And you've got a big ship, nice thick armor, because we like shielding. And I'd want a big crew, because actually what I know is that for this kind of range of medical problems, including psychological and mental issues people will be experiencing, you don't get one doctor who can really deal with these things that well. You're also going to want a dentist. So you're going to want a medical team, and that's not counting wanting nurses. Trust me, if you've ever come across group of doctors trying to do things on their own, you suddenly realize why you want nurses and operating department practitioners and other people. So I'd actually want a big, big ship to go, and that would mean that you'd get the water, you'd have space for things, and you'd have a lot less issues with crew dynamics, and you'd have a lot more redundancy, both in terms of personnel and in terms of equipment, and the ability to manufacture and fabricate things. So you'd want the engineers to do that. So actually, I think going as far away, and that's what they had on these ships. They had a ship's carpenter. You know, look at an old Age of Sail ship. You had a ship's carpenter. You had a ship's sailwright. You had all these sorts of people. You had the surgeon. You had you had the surgeon, but realistically, they oh god, I mean, the medicine back then was just horrific. You had all these sort of people who were there to keep everything going, and that way you can actually have some supply specialists as well, because organizing, coordinating, planning logistics, and then dealing with it is not necessarily going to be easy. And if you've got a big ship, and that way the science can focus on the science, and you're not asking somebody to be a scientist and a medic and a communication specialist and program computers and things. I mean, yes, there might be a few people who are like that, but they're weird. And do you really want to be on a team with somebody that weird? No, I'd rather go on a big ass ship that is full of people. So that's space medicine. Now, so I want to go in a nice big ship, and yeah, nice big ship, heavy armor, water for armor. God, this is sounding like a 1930s, 1940s battleship. I want a torpedo protection system with spaces, with air, fluid voids to absorb the badness, so that whether that's cosmic rays, background space radiation, galactic space radiation, solar flare damage, or micrometeorites. I'd like a couple of inches of steel, please, and then some water, and then a void space, which we'll fill with probably a little bit of low density air, and then some more water, and then metal, and we'll do that, and I'll sit inside all of that. And yeah, I mean, the only problem is that is going to weigh a lot more than 130 tons to take off. So what we're going to need is a better form of propulsion. So over to the rocket scientists. Ciao.